This program is brought to you by Stanford University. Please visit us at stanford.edu.
Well, tonight is our last class for this quarter, and I am not going to have time to do all the things that I would have liked to do. What I'm going to do is show you what I will do is tell you where the basic things of electrodynamics come from. You can go home, you have enough information, you can go home and work out the equations by yourself. I will try to sort of outline clearly where the various components come from and where they go. The basic principle is always the principle of least action. But in order to use it, you have to know what the action is. The action is typically an integral of a Lagrange density over all space-time. So before I do anything else, let me just remind you, if you have a Lagrangian, and the Lagrangian is composed of some collection of fields, let's just call a generic collection of fields. I don't want to use phi because what's a good F. F stands for field. And there may be a whole bunch of them, so let's label them F sub A. A now is not a space-time index. It doesn't refer to dimension. It just could be the first field, the second field, the third field. It could run over fields of very different type. For example, as A varied, one F might be a scalar field. Another F might be a vector field, like the vector potential. So this is very generic. A collection of fields which depend on x and t. Or in a relativistic notation, they would depend just on the four components of space-time. The Lagrangian, in general, is a function of the f's, all of the f's, and their first derivatives with respect to the x's. So the Lagrange density is a function which depends on the derivatives of f with respect to the various directions. There are four of them for each a, fa. So this notation is just meant to indicate that the Lagrangian can depend on all of the first derivatives of any one of the fields f, and also the undifferentiated fields f also. For example, in the scalar field Lagrangian that we studied, the Lagrangian was the sums of squares or differences of squares of the derivatives of f with respect to x. And then we also threw in another term, which I called the mass term, which just depended on the field itself without derivatives. So this is the general form. The action is the integral of this thing over all space-time. But just as for a single particle, when you think about a single particle and you ask what the implications of the principle of least action are, you can either think about the whole thing globally, or you can just think locally, and you can say, what implications are there for what are going on in the vicinity of a point? What are the implications of the principle of least action? And the answer is Euler-Lagrange differential equations, which you would call field equations for a field. I'm not going to derive them. I'm just going to write down what the general form is. Before I do, let me write down the form, the ordinary form of the Euler-Lagrange equations for the motion of a particle. If you have a particle with a set of particles, instead of having Fa, we would have a set of coordinates xa, and the Lagrangian would be a function. This would be now, it's not, the Lagrangian would be a function of L of the time derivative of x, that's the velocity, and the x's themselves. Okay, so the Lagrangian in this case is a function also of derivatives, now of fields, not coordinate positions of particles, and also the field itself undifferentiated. It's similar to this. That board is a generalization of this board in which there is not one independent variable that a coordinate can depend on, but 4 independent variables that a field can depend on. Okay, let me just remind you what the Euler-Lagrange equations are. They say first differentiate Lagrangian, no, I better call this square Lagrangian, L, with respect to the velocity of the 8th coordinate, not 8th as in 1, 2, 3, 4, 5, 6, 7, 8, but 8th as in little a. You take the Lagrangian and you differentiate it with respect to the derivative of the coordinate. In this case, there's only time derivatives. Then you differentiate that with respect to time. That's the left-hand side of the Euler-Lagrange equation that follows from the principle of least action. And the right-hand side is just the derivative of the Lagrangian with respect to xa. How many such equations are there? There's one, oops, this should be x sub a. There's one such equation for each value of little a. So if there are 100 coordinates, then there are 100 equations. And of course, these equations are nothing but Newton's equations for the several coordinates describing the particles in the system. The analog on this side is very similar. This time, you have a set of derivatives, not just a time derivative, but also space derivatives. The first thing you do is differentiate the Lagrangian with respect to the derivatives that appear in it. Now, can you differentiate something with respect to a derivative? You bet you can. We just differentiated the Lagrangian with respect to a time derivative. In the same way, we can differentiate the Lagrange density with respect to what it depends on, which is the partial derivative of fa with respect to x mu. There are several such derivatives, and so there are several terms like this for each a. We're focusing now on one value of a, just as we focused on one value of a over here. That's the first thing. It's the analog of the derivative of the Lagrangian with respect to the velocity. Then we have to differentiate that, not with respect to t in general, but with respect to x mu itself. So we differentiate that with respect to x mu. Now this left-hand side, for each a, is really a sum of 4 terms. Let me write it out explicitly, or almost explicitly. It's the derivative with respect to time, which I'll call x naught, of the derivative of the Lagrangian with respect to the time derivative of fa. This is the time derivative of fa. We could have also called this d by dt of the derivative of the Lagrangian with respect to f dot. In other words, the analog of this. But then there were more terms. There was also, remember the Einstein summation convention, whenever you see a repeated space-time index like that, it means you sum over it. So there's also derivative with respect to x1 of the same kind of thing, derivative of the Lagrangian with respect to derivative of fa with respect to x1, and so forth and so on for the other 2 coordinates. That's the structure of the left-hand side of the Euler-Lagrange equations. The right-hand side, we just differentiate the Lagrangian with respect to fa. So that's equals the derivative of the Lagrangian density with respect to the field itself. Yeah, the dots belong, don't they? This is of the form, typically this is a wave equation. It's typically a wave equation. If you work it out for the little scalar field Lagrangian that we've worked out several times, you'll find out this is just the good old wave equation for the motion of ordinary waves. It's the analog of this. And having said it, Now let's put it up here. That's the way we derive equations of motion, differential equations, from the principle of least action. What equations are we interested in? We're interested in Maxwell's equations. We've already worked out the equations of motion of a scalar field. Let's come now to Maxwell's equations. Let me just write down what they are. There are plenty of different conventions and units. I'm going to write them down in a sort of unit-free way where I have there's perfectly good units. I forget which ones they are, where all the 4 pi's don't appear in the equations. They appear someplace else. They appear in the solutions of equations, various constants associated, what is it called, mu and epsilon. They're all set equal to 1. Are they called rationalized units? I always forget. But here they are. Here's Maxwell's equations.
Sounds rational.
Yeah, it is rational. All right, what are the equations for? The equations are for the electric and magnetic field. All right. The electric and magnetic fields are fields, obviously. They depend on space. How many of them are there altogether? 6. 3 components of the electric field, 3 components of the magnetic field. The electric field is E. The magnetic field is B. I have no idea what the history of B for magnetic field is. I don't know. Why it wasn't called M, I don't know. Yeah, I suppose it was mass. So I don't know why, but we're stuck with it.
You know, the last lecture we spent some time, adding a term to the partials to show how to restore gauge and gauge.
Yes, we're going to talk about that more.
Okay.
Right, we're going to talk, but here's the target. The target is what you want to get. And then we're going to go back to the Lagrangian and the invariances and all that stuff and see how we would go about getting this from the principles. Lagrangian, Euler-Lagrange equations should produce Maxwell's equations.
And it's just a regular partial up there. It's not no gauge term added to it or anything. So just a regular.
Where?
Oh, never mind.
These things could involve the gauge fields. I mean, that's very general. Right. Okay. Incidentally, the electric and magnetic fields are not the fundamental fields like Fa in this formula. The electric and magnetic fields are more like the derivatives of the fundamental fields with respect to the coordinates, but we'll see why. Anyway, here's where we want to get to. Everybody remember Maxwell's equations? I remember them up to a sign. All right. Divergence of the electric field. Anybody not know what a divergence is? Good. Then I don't have to write down what a divergence is. The divergence of the electric field, this is, of course, derivative with respect to x of the x component of the electric field plus derivative with respect to y of the y component, etc. Right? 3 terms. That's equal to what? Rho, the charge density. In some people's version, there's a 4 pi in there. In mine, there is no 4 pi. Anyway, del dot E is equal to rho. The curl of E, everybody know what a curl is? No. Who said no? Out. Do you mean it, or shall I explain it, or? You do or don't?
I do. I didn't say no.
I know. Somebody said no, but I couldn't hear who it was. All right, I will tell you what the curl of a vector field is. But we'll have to do it fast, because, all right. Anytime you see the upside down triangle, it means it's a derivative of some sort. Okay? You said you did know what divergence is. Yes or no? If not, I will write it down. Okay. If you have a vector field, in this case, a vector now means a 3-dimensional vector. It has three components. Let's call them, let's be very, very specific now, x, y, and z. The x component of the electric field, the y component of the electric field, and the z component. All right. The divergence of the electric field is a measure. Remember, the vector field is a vector at every point in space. And so at every point in space, it points in some direction. And the divergence is a measure of the spreading of the electric field away from a point. For example, a typical vector field that has a divergence would point away from some point like that. It's diverging. That's, all right, now the mathematical expression that represents this tendency of the vector field to point away from a point like that is called a divergence. It's del dot E, that's the notation for it, and it stands for the derivative of the x component with respect to x plus the derivative of the y component with respect to y plus the derivative of the z component with respect to z. Definition. But it does have this property that it tends to show you that something is spreading away from a point. Of course, yeah, okay. That's the notion of divergence. Now there's another notion called curl, which is also a kind of geometric notion. It tells you if you take an axis, now a three-dimensional axis, this is a three-dimensional idea. When spreading away from a point is a three-dimensional notion, spreading away in all three directions. The curl is also a three-dimensional notion, but it itself is a vector. The curl itself has three components. All right? And each component is related to an axis. And what the curl is given an axis, let's say the axis out of the blackboard, it represents the tendency of the vector field to sort of wind around that direction. It's, if we thought of wind velocity as the relevant field, then a tornado would have a large curl. Right at the center of the tornado, the velocity field, the wind velocity, would be circulating around a point. A hurricane would have a large, sometimes it's called vorticity, but curl is the right term. And I'm going to write down what the formula is. So let's call this axis the z-axis. No, let's call that axis, yeah, let's call that the z-axis. Then the symbol for the curl is del cross E. It's related to the concept of cross product. And I'm not going to go through cross product today, but I'm going to assume you know what it is. But in this particular case, I'll write down exactly what it is. It has in itself, it has three components. So let's take the z component of it. The z component, and this is the thing which represents the tendency of the field to wrap around or to circulate around the z-axis. Obviously, we could also think about the tendency to circulate around the x-axis or the y-axis. That's why there's three components. And this is given by the x derivative of the y component minus the y derivative of the x component. That's the z component of the curl. And as I said, it represents the tendency of the field to wrap around that direction like that. And now if you want to go to the other two components of it, you just cycle through. Cycle in the following sense. X, Y, Z. X goes to Y, Y goes to Z, Z goes back to X. So here's what I mean by that. You go to the next equation by substituting for Z, X, for X, Y, and for Y back to Z. So here's what it would look like. Del cross E, all right, Z cycles to X, so put an X there, is equal. Now X goes to Y, so that's derivative with respect to Y. Y goes to Z, minus dz EY. And what would be next? You cycle once more through the 3 letters of the alphabet. Del cross E, the y component, z, x, y, is equal x, y, the next one will be z, y, z, next is x, and minus dx, ey, dx, ez. These are the 3 components of a curl. So this is an operation that you do on a vector and gives you another vector. This is an operation that you do on a vector and gives you a scalar. All right? One of them gives you the tendency for the field to separate out from a point. It's a scalar, the divergence. And the other has 3 components, the circulation of the field around the 3 axes, basically. Okay. Now, Maxwell's first equation is del dot E equals rho. This is the equation that tells you that charge densities make electric fields. For example, it's at the root of the fact that if you have a point electric charge, an electric field radiates out from it. So what it says is that the charge is a divergence of the electric field. Okay. Now, the corresponding equation for the magnetic field is del dot B, and what you might think you should put on the right-hand side is some density of magnetic charge. Well, what does magnetic charge mean? It would mean a little particle which we call a magnetic monopole. A magnetic monopole would be a particle that the magnetic field lines would radiate out of. There are no known particles like that in nature, although every physicist of my particular persuasion, meaning my particular subject rather than my particular belief system, almost all theoretical physicists engaged in the subject of particle physics and so forth believe that magnetic monopoles really do exist. Just to see what's involved, imagine a bar magnet. A bar magnet has a north pole and a south pole, and out of the north pole comes magnetic field lines, and the magnetic field lines look something like this. You've all seen this. You take a magnet, put it under a piece of paper, sprinkle some iron filings on it, and you make something like this. Now, if you take the south pole very, very far away, extremely far away, and you look just at the north pole, what you would see, let's take that south pole and bring it to Australia, way off the blackboard, what you would see in the vicinity of the North Pole would look very much like the field of an electron or a charged particle, except that, of course, it would not be an electric field, it would be a magnetic field. Magnetic field. Radiating out away from the North Pole. So you might think the North Pole then is the divergent, or the North Pole is behaving like the divergence of the magnetic field. But if you look more carefully, what you find is that there's also a magnetic field running right through the magnet, right through the magnet like that. And then in fact, the magnetic field is coming in here. In other words, the magnetic field lines run right through the magnet and then radiate out away from the North Pole. There really is no divergence to the magnetic field. What comes in goes out. So it really doesn't have a divergence like the electric field does. The electric field really does radiate out away from an electron. This magnetic divergence here is just because we didn't look inside the magnet. There are no known sources of magnetic field which are point sources in the sense that the field radiates out away from them in all possible directions. Here, in and out. So the divergence of the magnetic field is 0. Magnetic fields don't have divergences, at least not until somebody discovers a magnetic monopole. Now, you can fool your friends. You can get yourself a very, very thin magnet. There's another thing which will make a magnetic field, a solenoid. If instead of a magnet, you make an electromagnet, in other words, you just wrap a wire around an axis like this and let current go through it, then the magnetic field lines go through the solenoid and out the end here. Now you make yourself an extremely thin, flexible solenoid. And you grab a hold of this end and you bring it to your friends and you say, look, I have a magnetic monopole. Yeah, you can fool your friends into thinking you have a magnetic monopole if you could have a solenoid which was so thin that it could pass between atoms and so forth. That's actually what a magnetic monopole is. It's a magnetic charge which is, in some mathematical sense, really connected to an infinitely thin, infinitely light, infinitely flexible solenoid. But until somebody discovers a real magnetic monopole, the right-hand side of this equation is 0. All right, now we also have equations for the curl of the electric field. The curl of the electric field. Now what's the curl of the electric field equal to? The time derivative of the magnetic field. This says that a changing magnetic field, if the magnetic field in space changes, it necessarily creates an electric field. If B dot is not 0, in other words, if the magnetic field is changing with time, it creates an electric field. For example, supposing we started, let's take a solenoid, but let's make it infinitely long in both directions. I'm not particularly interested now in this monopole problem. We take the solenoid infinitely long. We start with no current in the solenoid, so there's no magnetic field. Then we start increasing the magnetic field. We start increasing the current. Increasing the current creates a magnetic field through the solenoid. As we increase the current, the magnetic field increases, and for that reason, it generates an electric field. The electric field has a curl. So it wraps around. What does it wrap around? It wraps around the solenoid. So ramping up the current through a solenoid creates an electric field around the solenoid. And in fact, in particular, that electric field could accelerate a charged particle and get it moving in a circle. All right, that's the meaning of this equation. Whose law is this, that a changing magnetic field makes an electric field? I always forget. That's one of Faraday knew it. I'm not sure. I can't remember which one is which. Okay, that's the magnetic field making electric field. And there's a similar equation for the magnetic field. The curl of a magnetic field is related to the time derivative of the electric field. Minus sign in this case, a minus sign, electric field dot. So this says a changing electric field will also make a magnetic field. For example, you take a capacitor plates over here connected to wires. If the capacitor plates have charge on them, then there will be an electric field between the capacitor plates. Now we can start with an uncharged capacitor and pump some electric charge into the capacitor plates. And so in that way ramp up the electric field. Ramping up the electric field must make a magnetic field. And in fact, the magnetic field has to wrap around something. It wraps around the direction of the electric field lines. All right, so ramping up the charge in a capacitor temporarily creates a magnetic field, and that magnetic field would orient a compass. So a compass would respond to a changing electric field in this manner here. This is not the complete equation. There's another thing on the right-hand side. What is it? The current, not the charge density, but the current. The current density, J. Both sides of this equation, in fact, both sides of this equation are vectors. The curl of the electric field is a vector. The magnetic field is a vector. The curl of the magnetic field is a vector. The electric field and its time derivative are also vectors. And the current is a vector. Now, this is the three-dimensional current. Remember let me just remind you what that current means. The three-dimensional current, if you take a little window in space, oriented so that the perpendicular to it is along some axis, then the amount of charge passing through the little window per unit time, per unit area, is called the component of J in that direction. So it's the electric charge passing through a little window in space per unit time, per unit space. And the reason it's a vector is because you can orient that little window in different directions, and in that way sample the current going in different directions. All right, so that's J, and that's on the right-hand side. Now what that says is how do you get charge to get onto these capacitor plates? Well, there's only one way, and that's to send a current into them, right? So you have to send an electric current into here. That will charge up the capacitor plates. And during the time that the capacitor plate is being charged, there is a current in here. That current, even in places, let's say far away from where the electric field is, from the capacitor plates, let's go way out here, there's an electric current going through here, and that electric current also makes a magnetic field which winds around here like that. So it's kind of interesting. Here's the picture. You can have an interrupted place where the current cannot flow, and in that way make a capacitor plate like this. You can make the capacitor very long. The flow of current, as it's ramping up the capacitor, makes magnetic field lines which wrap around the wire, but it doesn't stop at the place where the current ends. It continues, the magnetic field continues into the region in the gap here, and it continues because the right-hand side contains both the time derivative of the electric field as well as the current. This term has incidentally, Faraday didn't know about this term. He only knew about this. He knew that a current makes a magnetic field, okay? Maxwell realized actually that there was not an ambiguity, an inconsistency in the equations without this term here, and Maxwell put that term in. It's called a displacement current.
Okay.
I don't know who's being displaced.
I think that one is Ampere's law.
Yeah.
And that one is
Well, with the J, it's called Ampere's law.
And with the okay.
This is called a displacement current.
Okay. Well, according to this,
Yeah.
You've got the sign of E and B backwards.
Always happens. Now am I better?
Yeah.
Good. Of course, that can be absorbed into a change of definition very easily, but if you change the definition of the sign of the magnetic field, it won't change this equation.
Yeah.
It'll change this one and change its sign, and it'll change this one and change its sign. And then you can change J by changing the definition of which is positive and which is negative electric charge. So there's no real content in.
Same thing with you've got the sources and sinks.
Yeah.
Positive and negative. And
Yeah.
which one is really
That's
the
right.
source and sink?
That's right. So the signs there are conventions, but once you fix them, you fix them. Who was it that fixed the convention about positive and negative charge? Benjamin Franklin. Yeah. course, he had no way of knowing what it was that was actually flowing in the wires. There was no way that he could know that the electron was the fundamental charge carrier. He called the current negative, meaning to say a flow of electrons in a certain direction. He called arbitrarily a negative flow of current. And the result of that has been hundreds of years of confusion among yeah, I have to explain this. Every time I teach elementary electromagnetism, I have to explain, and it drives everybody crazy, that a flow of electrons this way corresponds to a current that way. Ben Franklin did some good things, but that wasn't one of them. Okay. Now, we want to try to get these equations. Oh, there's one more equation which is central to electrodynamics. These equations tell you how the charges and currents, the charge and the flow of charge, create or affect the electromagnetic field. The other side of the coin is the way the electromagnetic field affects the charges. And it affects the charges by exerting forces on them. So the other side of the coin is the force exerted on a charged object due to the electromagnetic field. All right, so let me write down what that force is. It's called the Lorentz force law. And it's the force on a charged particle is equal. First of all, there's the electric charge of the particle. Let's call that E for electric charge, measured in some units. And our purpose now is not to worry about units. They're measured in coulombs, and the charge of an electron is a horribly small number of coulombs. What is it? I don't remember what it is. Something like that. 10 to the minus 19 coulombs for the electron, yeah. So that's a very small number. But for an electron, for some other object, it may be of order, it may be bigger. Incidentally, 1 coulomb of charge is a huge amount of charge. If you put 1 coulomb of charge on a basketball, the effect of the repulsion would just blast it to smithereens. So a coulomb of charge is a lot of charge. But the force is proportional to the charge on a particle, and then there's 2 terms. One of them is just the electric field. The force is proportional to the electric field, the factor of proportionality being the electric charge. So first of all in here, there's the electric field. Incidentally, both sides are vectors in the 3-dimensional sense, force and electric field. Then there's another term which is absent unless the electron or the charge is moving. So a stationary electric charge, this is all there is. Then there's a velocity-dependent force, and it's plus the velocity of the particle cross product with the magnetic field. So it's proportional to the product of velocity and magnetic field. It points in the direction perpendicular to both the velocity and the magnetic field. So if we have a magnetic field, let's suppose there's a magnetic field pointing into the blackboard. Magnetic field pointing into the blackboard we usually represent by a bunch of little crosses. The idea, I'm told, is that magnetic fields are arrows. And looking at the arrow from behind, you see the feathers. So here's the feathers. All right? If you want the magnetic field to come toward you, you just see the points of the arrows. I'm told that's where this convention comes from. All right, so here's a magnetic field pointing into the blackboard. V cross B, if you don't know what a cross product is, I'll rough it out for you now, but not with mathematical precision. It's first of all a vector which is proportional to the velocity, proportional to the magnetic field, and in the direction perpendicular to both of them. So for example, if it's proportional to the electric and magnetic field. It's also proportional to the sign of the angle between the electric and magnetic field. Sorry, between the velocity and the magnetic field. That's what a cross product is. So if the velocity is in the same direction or opposite direction to the magnetic field, there is no force. The sign of the angle between the velocity and the magnetic field is 0. If the charge is moving in this direction, then the force is perpendicular to both the magnetic field and to the charge. There's only one direction that's perpendicular to both of them, and that would be the vertical direction. I can't tell. Is it upward or downward, V cross B? Upward. All right, so a charged particle moving through here, if it were moving with a velocity v, would have a force on it which would bend it upward. The faster it moves, the larger the force. The larger the magnetic field, the larger the force. That's this term. This is called the Lorentz force law, electric and magnetic forces. This term is velocity dependent. This term is not velocity dependent. That's what we would like to get out of a fundamental theory of electromagnetism. So what do we need to do? We need to find ourselves a Lagrangian which, when we subject it to the principle of least action, will give us these 1, 2, 3, 4, 5 equations. Now, how many equations are there? There's a lot more than that. This is one equation. This is one equation. One equation. One equation. How many is this? This is 3 equations. And this is 3 equations. So these are the field equations. That's 1, 2, 6, and 2 is 8. 8 equations. And, say it again? And 3 equations for the force law, yeah. 3 equations for the force law. And we'd like to derive them from a principle of least action. Why? Among other things, it's the principle of least action which guarantees that there's a concept of energy. If, in the theory of electromagnetic forces and electromagnetic field, there was not a good concept of a conserved energy, there sure wouldn't be any concept of conserved energy in the world, because so much of physics has to do with electric and magnetic forces, almost everything in our electric, magnetic, and gravitational. And the only thing in the basic principles of physics that guarantee that there's a concept of energy and momentum is the principle of least action and the formulation of mechanics and field theory in terms of a Lagrangian. So it's not just because it's pretty, or not just because we like ideas like the principle of least action. It is really important to derive theories from a principle of least action, because if you don't, none of the rules about the connection between symmetries and conserved quantities make any sense. The connection between symmetries and conserved quantities, that includes energy conservation, momentum conservation, charge conservation, all of those things are dependent on the principles of mechanics that are embodied in the Lagrangian, or in the principle of least action. Okay, so let's try to invent a theory of electricity and magnetism assuming some basic principles. Two basic principles, really. I'm not sure in which order to write them down, so I'll write them down in the order that we learned about these things. And they're quite independent. The two basic principles are, first of all, Lorentz invariance. In other words, Lorentz invariance, in other words, the special theory of relativity. All right. It's all this and this alone which guarantees, for example, that the speed of light is the same in every reference frame. Lorentz invariance includes rotational invariance. And so this is the basic symmetry of space and time, if you like. It also includes the idea that things don't depend on the position that you do the experiment. If you translated everything, it would stay the same. If you rotated everything, it would stay the same. If you subject it to a velocity boost and examine a system from a moving reference frame, it should stay the same. It should have the same consequences. All right, so Lorentz invariance is one basic principle. And Lorentz invariance is very simple from the point of view of the Lagrangian. All you have to do is make sure that the Lagrangian density is a scalar. That's all. So it's easy. Right? So Lagrangian density should be a scalar. Next, a little less familiar, but also not very difficult, is gauge invariance. Gauge invariance. Gauge invariance. Let me remind you about gauge invariance. Where it came from was requiring that a certain scalar field Lagrangian should be invariant when we did this kind of change of phase, the e to the I epsilon, and that epsilon be a function of position. But let me remind you what the bottom line in the end was. The bottom line in the end was that we had to invent, in order to implement that symmetry, we had to invent the idea of a vector potential. What we had to do was replace the derivative of the scalar field with respect to position, which is not invariant under gauge transformation. If we multiply the scalar field by e to the I epsilon of x, then in taking the derivative here, there are terms with a derivative of epsilon just not invariant. What do we have to do? Anybody remember what we had to do in order to make the Lagrangian of the scalar field gauge invariant?
You have to add another term.
Right. We had to change from the ordinary derivative to what is called the covariant derivative. You have to add to this plus I e vector potential times phi. If at the same time that we multiply phi by e to the I epsilon x, if at the same time we transform A to A plus the epsilon by dx, and I think I should have a 1 over electric charge there. If we change the vector potential in this way, whenever we do such a transformation, then this covariant derivative, this so-called covariant derivative, doesn't change. It's invariant. So if we build our Lagrangian, instead of just out of d phi by dx, the covariant derivative, this incidentally is often represented as d mu phi, if we build the Lagrangian not wherever we originally saw the derivative of phi, we write the covariant derivative of phi, then the Lagrangian is gauge invariant. But that was the origin of this idea of a vector potential. The vector potential is necessary to soak up the change that would happen in the ordinary derivative when we multiply by e to the I epsilon of x. All right, but now that we have A, we can ask, first of all, what kind of Lagrangians can we cook up which are gauge invariant? What kind of Lagrange densities can we cook up that are gauge invariant? Before we do that, we should ask what kind of structures, what kind of combinations can we make that are gauge invariant? And the simplest answer, the simplest thing that we can make, which is gauge invariant, out of A, what is A? How many components does A have? 4. Time component also. This is a 4 vector. Its fourth component, its time component, is the electric potential, is what's usually called the potential. But in any case, there are 4 components. The 3 of them, the 3 space components, are often just called the vector potential. But in a relativistic setting, there are 4 components to the vector potential. Okay, so A then has an index which runs over the usual space-time indices. A itself is not gauge invariant. How do I know? Because it transforms. It changes when you do a gauge transformation. It goes to A plus something. So A is not gauge invariant. But to make a long story short, the simplest thing which is gauge invariant is a tensor, a thing with 2 indices, a mu index and a nu index. And here it is. You differentiate the muth component of A with respect to the nuth component of position. This means derivative. For example, this could contain something like derivative of AX with respect to Y. The nu would correspond to Y, mu would correspond to X. There are also terms for time components, but let's just write down. That's a thing with 2 components. It is a tensor, but we don't really need to know what a tensor is for these purposes. It is what it is. Derivative with respect to nu of A mu. Now, what happens to this object when you subject A to such a transformation? What happens is it picks up an extra term. So let's look at it. Here's A mu. What about the derivative of A mu with respect to X nu? What it does is it just goes to d nu A mu plus 1 over E, and then the second derivative of epsilon with respect to X nu with respect to X mu. The second partial derivative with respect to nu and mu. This is the change that happens when you do a gauge transformation to this particular combination. This is not gauge invariant, it changes. But notice that this change here is symmetric under the interchange of nu and mu. The process of differentiation, it doesn't matter which order you differentiate. Process of differentiation with respect to 2 coordinates commute. Commute means it doesn't matter which order you apply those 2 operations. And that means that if I subtract from this minus d mu A nu, this term will cancel. Why? Because this term is symmetric when I interchange mu and nu. And so when I subtract the same object with the opposite ordering of mu and nu, or the opposite dependence on mu and nu, this term will cancel. And the result is that this object, d mu A nu, which is called F mu nu, that's gauge invariant. It will not change when you do a gauge transformation. How many such objects are there? How many components does it have? Well, offhand, mu and nu can run from 1 to 4, so it looks like there's 16 independent components of F mu nu. Not so. And the reason is that this is antisymmetric. If you interchange mu and nu, it changes sign. So that means, for example, that F12 is just equal to minus F21. F13 is minus F31. So the different components of F mu nu are not independent. It's antisymmetric. How many components of an antisymmetric matrix are there in 4 dimensions? All the diagonal components are 0. In other words, if nu and mu are the same, these 2 terms will cancel. F11, what is F11? If F11 is equal to the derivative with respect to x1 of a1 minus the derivative with respect to x1 of a1. So it's 0. The diagonal elements are all 0. And the off-diagonal elements have opposite sign when you interchange the two indices. So how many of them are there altogether? 6. 6. 6 independent, you can think of it as a matrix, a 4 by 4 matrix, 16 to start with, 0 on the diagonal, and off diagonal, the off diagonal, there are 6 off diagonal above the 6 over there and another 6 over here, but the other 6 over here are just the negatives of the ones over here. So there are 6 independent components, and those 6 independent components are nothing but the electric and magnetic fields, the components of the electric and magnetic fields. Let me write them down for you. We start with F. Let's start with F01. By definition, this is the derivative with respect to x naught. X naught is time, so it's just a time derivative of A1. 1 could stand for the x component. So F naught 1 would be derivative of A1 with respect to x naught minus the derivative of A naught with respect to x1. Same thing if I replace 1 by 2 and 3. So there are 3 components which are of the form F naught x, y, or z. Those 3 components form the electric field. This is E1. The x component of the electric field would be the derivative of the x component of the vector potential with respect to time minus the derivative of the time component of the vector potential with respect to x1, with respect to x. So that's we have 3 components of the electric field. And now we also have 3 additional components. Let me tell you their connection with the magnetic field. That's a little, this one was sort of obvious, easy, if not obvious, easy. The other one is also not difficult. First of all, F12. That's got to be, for example, the xy component. Let's use x and y now. I'm only interested in space components now. And the other 3 components do not involve a time index. Why not? Well, these 3 involve the time index. The only thing else, the other thing that could involve a time index would be F00, and there is no F00. So the other 3 components involve pairs of space indices. For example, Fxy, and I'm now using x for 1 and y for 2, just to be specific. Fxy is equal to the derivative, let's see which way it works, derivative with respect to x of ay minus the derivative with respect to y ax. Now, the only thing that's left is the components of the magnetic field. So this must be some component of the magnetic field. Which component of the magnetic field? Z. We have by some sort of symmetry, how could it could only be the Z component. And it is the Z component. So this is the Z component of the magnetic field. And then to get the other ones, you just cycle again. X to Y, Y to Z, Z back to Y, Z back to X. So Fx, YZ, that's equal to dyaz minus dzay. And that's what? That's B, what comes after Z? X. And the last one, Fxyz, yzx is equal to xyz, yzx minus dot, 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 and that's equal to by. So this is the connection between, this also says that curl of A, another way to write this is that curl of A is equal to B. All right, so that's the other electric fields involve a time component and a space component. They also involve a time derivative. But the magnetic field never has a time derivative in it. It only has space derivatives in it. Okay, that's the electromagnetic field tensor. And the important thing about it is that it's gauge invariant. In fact, it's the simplest thing that you can make up out of the vector potential that is gauge invariant. Yes?
Is there any condition on A at all?
Not at this point.
At this point, A is just an arbitrary.
Arbitrary vector field. Well, apart from smoothness and differentiability, right. No condition on it. In fact, there's an ambiguity in its definition because you can always do a gauge transformation on it. So it's quite free to vary in any way. Okay. Now we want to build a Lagrangian. Lagrangians typically involve fields and their time derivatives. Fields and their various derivatives. The field A by itself, if undifferentiated, is not gauge invariant. There's no way to put into the Lagrangian the field undifferentiated without destroying the gauge invariance. A by itself is not gauge invariant. You can make the Lagrangian out of any combination of the f's. Anything that involves f is gauge invariant, since f itself is gauge invariant. Gauge invariance is not enough to tell you what combinations of f's to put together in what form. The other thing that goes in is Lorentz invariance. If we have f mu nu in our Lagrangian, and we want to make a scalar, the simplest scalar that we can make is just to multiply it by f mu nu again and contract the indices in the way that we've learned how to do some Einstein summation convention. As long as the indices are contracted, contracted means just summed over when they're repeated, we make a scalar. All right? There's in fact a minus a quarter, but that's mostly convention. There's a minus a quarter, but as I said, that's simply a convention, and of course, whenever anybody puts a minus a quarter in a thing like this, you know that what it does is it removes a 4 from some later equation. And it does. It removes 4s from Maxwell equations there. But it's arbitrary. It could be absorbed into changes of the electric and magnetic field. So it's not important. The important thing is that it's gauge invariant because it's made out of F, and it's Lorentz invariant because its indices have been correctly grouped and summed over. That's the Lagrangian of the electromagnetic field. Okay? Lagrangian density. And what is it? Let's write it out. 1 over 4 partial derivative of A mu with respect to x nu. Remember what indices upstairs mean. They mean exactly the same thing as indices downstairs, except for the time component where you change sign. So for example, if there's a time component in either mu or nu, then it flips sign relative to the original definition of f mu nu. So it's just a question of signs, whether the indices are upstairs or downstairs. Minus d mu a nu. That's the field tensor with the upstairs indices. Okay. And we multiply it by the field tensor with the downstairs indices. D mu. Do I have it right? I think I might have the mu nu. I think I should have mu and nu. Nu and mu. This stands for various squares and sums of squares of various components of the electric and magnetic field. I'll write it out in terms of the electric and magnetic field in a moment. But let me just point out what it is. It's a thing which is quadratic in various derivatives of the field. In that respect, it's not so different than d mu phi d mu phi. It's quadratic in derivatives. It's more complicated because it has more components. But again, each term is something which is the product of a derivative of a field times another derivative of a field. So this is a Lagrangian which involves quadratic expressions, in other words, things which are products of two field derivatives, summed in various ways. So it's not so different than previous Lagrangians that we've studied. In the case of the scalar field, without violating any symmetry, or I think we had a star here, for example, in the case of the complex field, we were also able to add m squared phi star phi, maybe minus. There is nothing that we can add to this that doesn't involve derivatives of the field. Something like adding a squared or something like that, no good. A squared is not gauge invariant. Or a mu, a mu. You might think, well, why can't we add a mu, a mu? It's Lorentz invariant, but it's not gauge invariant. It changes when you let a go to a plus the derivative of epsilon. So this is not gauge invariant. Otherwise, it's perfectly good. Lorentz invariant, perfectly good. Perfectly acceptable Lagrangian from every other point of view, but it's not gauge invariant. So this is the Lagrangian of electrodynamics. Let me tell you what it has in it. Let's look at it. It has various squares, various products of the components of F. What is it? It's F mu nu, F mu nu. It's proportional to sums of squares or differences of squares, depending on which component we're talking about. It come in with a plus sign or a minus sign. For example, here's F naught 1, F naught 1. Now what is F naught 1 with lower index here? Anybody remember? E1 or EX. What is it with the upper index here? When you raise a space component index, nothing happens. When you raise a time component index, the sign changes. All right? So this is proportional to minus EX squared. Right? There's a minus EX squared. Well, there's another term here, which is F1 naught, F1 naught. But that's exactly the same thing. Why? Because F1 naught is just minus F. You know, this is minus this is minus this. The two terms here just double this. The dividing by 4, that makes it divided by 2. And then the minus here just changes it to plus. So the terms involving F naught 1, F naught 2, F naught 3, they just give you the sums of the squares of the electric field components. EY squared plus EZ squared. That's what's in the Lagrangian from the mixed space-time components. What about the space-space components? Again, minus a quarter. Let's look at one of them. The mixed space, the space-space components could have F12, F12. What is F12 times F12? First of all, what is F12? It's B3. B3. Maybe it's minus B3, I don't remember, but we're squaring it so it doesn't matter. Now, here I've raised both indices. 1, 2. What happens when you raise two space indices? Nothing. Okay? So F12 upper is the same as F12 down lower. And this is just B3. This is B3 squared. There's a minus a quarter. So I get minus a quarter B3 squared. Well, why is it minus a half and not minus a quarter? Because there's another term which is 2, 1, 2, 1. Exactly the same. So it's b3 squared divided by 2 plus b3 would be z squared plus dy squared plus bz squared. That's the x squared. The net upshot is the Lagrangian is simply 1/2 of e squared minus b squared. 1/2 the electric field squared minus the magnetic field squared. All right, so e squared minus b squared. It's a little bit funny. It involves the electric field and magnetic field sort of almost symmetrically, but not quite. One comes in with a negative sign, the other comes in with a positive sign. Let's look at the electric field again. The electric field involves, I'm going to be a little sketchy right now because we don't have time. But nevertheless, sketchy or not, the argument is correct. The electric field, which is F01, for example, contains things like derivative with respect to x0, that means derivative with respect to time, times A1. It also contains another term, but it's irrelevant for my argument right now. When I square it, this gives me some time derivative squared. Contains some time derivative squared. What kind of terms in the Lagrangian involve time derivative squared? Kinetic energy. Kinetic energy. So this is similar to the kinetic energy in the Lagrangian of a system. It's similar to the phi dot squared term, the time derivative of phi squared. It's similar to x dot squared. So this is the kinetic energy of the field. Now, when I say kinetic energy, I just mean it contains time derivatives squared. This contains no time derivatives. The magnetic field contains no time derivatives. Things which don't contain time derivatives we think of as potential energy. So this has the form of kinetic energy minus potential energy. That's exactly the way Lagrangians are supposed to look. It's analogous to the scalar field Lagrangian, which has phi dot squared, time derivative squared, again a half, minus the space derivative squared. The Lagrangian, exactly the same kind of structure, time derivatives squared minus things which don't contain time derivatives. What would you guess if you go through the procedures of constructing the Hamiltonian and then the energy? What would you expect the energy or the Hamiltonian of the electromagnetic field to be? Plus. So the energy in the electromagnetic field is just E squared plus B squared. If you work out, if we go through the entire apparatus of classical mechanics and so forth, we would actually discover that the energy, the Hamiltonian, is this, and the Hamiltonian is conserved. It's a general principle. And so this is energy. This is energy and its conservation. E squared plus B squared is conserved. Or not, should I say, is this the energy? Did I make a mistake? I did. I forgot to integrate it over space. That's the energy density. You integrate it over space. In other words, you account for all the degrees of freedom at each point in space, and that becomes the energy. So the integral of E squared plus B squared over all space is conserved. It's not conserved at each point of space. Energy can move from one point of space to another.
So without the integral, what we had originally was the Lagrangian density?
No, without the integral, it's the energy density. With a minus sign, it's the Lagrangian. Oh, yes, that's right. That's right. With a minus sign, it would be the Lagrangian density. And with a plus sign, it's the Hamiltonian density. But that just means the energy density. Okay. Now, next, the equations of motion. These guys here. I'm going to go again, sketch it. The equations of motion, what do? We take the Lagrangian. Where did I write it? I lost it. All right, so it's d mu a nu minus d nu a mu times d mu a nu minus d nu a mu. Incidentally, and I said there was a minus a quarter here, you can check yourself. If you leave out this term here, let me just leave it the way it is. All right. Let me give you an example of a piece that's in here. There's a term here which is derivative of, with respect to, let's say, x naught, a1 minus d1 a naught squared with a plus a quarter. Yeah. This, of course, is just the square of the electric field. All right. Let's take the derivative of the Lagrangian with respect to d naught a1. What is it? Can anybody differentiate this expression with respect to this argument here?
It only depends on the derivative, so it'd be 0, right?
No. We want to differentiate with respect to the derivative. We want to calculate the derivative of the Lagrangian with respect to d naught a1. In other words, with respect to this variable here.
Get rid of the square and put a 2 in there.
Right? Well, put a 2, but it cancels the quarter, so that's a half. I think this should only be a half here. There is only a half there. So the half goes away. And what else do you get? You get d naught a1 minus d1 a naught. The derivative with respect to this variable here, how do you do it? You just differentiate the square of something. It's just the square of something. You just differentiate, you get twice the something. That's it. In other words, it's just f naught 1. All right, that's generalizable very easily. I'll write down what the general formula is. If I differentiate the Lagrangian with question?
Oh, is that E1, EX?
It's E1. But let me write down the general formula. The derivative of the Lagrangian with respect to the derivative of a mu with respect to x nu. All right. That is nothing but, it's got two indices, mu and nu. What's it going to be? What could it be except for f mu nu? And it is. Just like we showed that the derivative of Lagrangian with respect to d naught a1 is f naught 1, the general formula of this type is just f mu nu. Now we can work out the equation of motion. What we're supposed to do is take each one of these derivatives. Here's an example. Here it is. That's the formula we're using. Okay, we take each one of these derivatives and differentiate it with respect to the same index that occurs inside the derivative over here. That means d by dx nu. So the Euler-Lagrange equations just become, do I have this? I think I have it right. Yeah. D by, just a moment, let me just, this is, yeah, I think it's right. I think I have a mistake here. Let's see. Yeah, some index belongs upstairs that, that's lower.
They don't match. You have a mu down, x mu downstairs and an x nu downstairs.
This is a lower index.
I guess that should be upward.
So, oh, so wait, so, yeah. I think it's F mu nu upstairs. Right? This is a lower index in the denominator, so that makes it an upper index. And this is a lower index in the denominator of a fraction here. Yeah, it's F mu nu, both of them upstairs. Okay? So what's our equation of motion? Differentiate with respect to x mu, F mu nu. That's the left-hand side. But what's the right-hand side? It's just 0. The Lagrangian doesn't depend on the vector potential itself. So that's it. Which Maxwell equations are these? These are this and this, without the J. I have not told you what to do if there's a current. If there's a current, the Lagrangian has to be modified a little bit. Okay. But without the current, how many equations are these? How many equations do I have here? 4 equations. 4 equations. How many equations do I have here? 1 equation and 3 more. That's exactly what these equations are. In particular, if you plug in for F, for example, let's take a little piece of it. Let's take d naught of F naught nu What else do we have? We have plus d1 of F1 nu plus d2 of F2 nu plus d3 of F3 nu. Right? This is what's on the left-hand side, and that's equal to 0. Let's see what's there. We have to pick a nu. Pick a nu for me. Which nu do you want to study? Okay, then if we pick 0, this will be 0 because F00 is 0. And this will be d1 of F10 plus d2 of F20 plus d3 of F30. What is F10? It's the first component of the electric field. So it's the derivative of the first component of the electric field with respect to x1 plus the derivative of the second component of the electric field with respect to x2 plus the derivative of the third component of the electric field with respect to x3. This is the divergence of the electric field. All right. So in the absence of charges, if we don't have any charges around, any charge density, that just becomes del dot E equals 0. Let's look at another one. Let's look at, let's see, we looked at the time component. Let's look at the 1 component. So now, let's look at the 1 component. If we look at the 1 component, we have derivative with respect to time of F naught 1. I'm setting nu equal to 1 now. So d naught, F naught 1 plus, now we have d1 F11, but that's 0. F11 is 0. And then we have plus d by dx2 of F21 plus d by dx3 of F3 3-1, I believe. Is that correct? I think that's correct. Okay, what's this term here? That's the time derivative of the electric field. That's this one. What's over here? Well, it's a little bit complicated, but what do we have? F21 is B3. So this is second derivative, the derivative with respect to x2 of B3, and this one, if you work it out, is the other term that corresponds to curl of B. Curl of B. So the Euler-Lagrange equations are two of the Maxwell equations. The other two Maxwell equations are identities. They are not equations of motion. They just follow from the definition of the electric and magnetic field. This is something you can check. I'll allow you to check it. They just follow from the fact that the electric and magnetic fields are defined in this way. You don't have to do any work. It just follows from the structure you've written down. If you work out the other components, 1 and 3. 1, 1, 3, 3, yeah. Okay. So this is an example then that the Maxwell equations follow from the Euler-Lagrange equations for an action. And that same action has a Hamiltonian that's associated with it, which is E squared plus B squared. So we have a package. The package just comes from the simple expression for the Lagrangian, F mu nu squared, just the simplest gauge invariant thing you could have written down, simplest gauge invariant, Lorentz invariant thing. And all of electromagnetism without charges, without any charges in it, all of it follows from this very simple minus a quarter. Well, here it is. Minus a quarter F mu nu, F mu nu. Okay, very simple. So while you have a load of equations here, complicated, it all boils down, or it all derives from one simple expression for a principle of least action, if you like. All right, the last thing I'm going to do is tell you how currents come into this. Now, we could just be thinking about charged particles. Charged particles are an example of a current. But let's imagine now that we have a 4-vector of current, J mu. J mu, now J mu is the electric current. In some way or another, it has to couple to the electromagnetic field. There must be terms in the Lagrangian which involve J mu. Why is that? Well, where is J mu in these equations? Here's the time component. This is nothing but the time component of J. And here are the space components of J. Here are the space components of J over here. So J enters into the equations of motion. It must enter into the Lagrangian. What kind of simple connection, what kind of additional term in the Lagrangian can we put in that involves J? J is a vector, a 4-vector. We've got to do something to soak up this index. What is there around? There's the vector potential. That's the only 4-vector that we have to work with. So let's try J mu, A mu. In other words, we just take the 4-dimensional product of J with A, sum it over the indices, and that becomes part of the Lagrangian of the electromagnetic field. Now, for all my purposes now, let's just imagine somebody gave us the current. They told us what the current was. I'm not going to, we don't have time to study the equations and how J varies. Let's just imagine somebody told us what J is. All right? Is this gauge invariant? So, what do you think? The gauge invariant or not?
You have to say how J is going to vary with the gauge.
we have to say something about how J, sorry, good. Things which are gauge invariant are ambiguous. You can change them without changing any of the physics. Gauge covariant, things which vary when you do a gauge transformation are not physically observable things. The physical observables are the gauge invariant quantities. Right? So the electromagnetic current is a observable quantity. It's not something that changes when you do a mathematical gauge transformation. So J is gauge invariant. It really is the flow of current. You can measure it. It had better not vary when you do a gauge transformation, otherwise it would be something which would be ambiguous. It's not ambiguous. So given that J is gauge invariant, is J a gauge invariant? Not obvious. In fact, obviously not. Except if J satisfies some special property. So let's see if it changes when you do a gauge transformation. Let's see, where can we do this? I guess we can do it down here. What happens to JA when you gauge transform A? J mu A mu will change to J mu A mu plus 1 over the electric charge times d mu epsilon. That's the way the vector potential changed. 1 over epsilon. In other words, J mu A mu changes, the change in J mu A mu is the change in JA is J mu d mu epsilon integral, I guess there's a 1 over electric charge. So the answer is, it's not gauge invariant. It has changed by this much. But now let me do a trick. The trick is called integration by parts. If you have an integral over space, or space-time, oh yes. Here's the integral that goes into the action. If we integrate it over 3-dimensional space, it's part of the Lagrangian. If we integrate it over 4-dimensional space, it becomes part of the action. The real issue is whether the action is gauge invariant, not whether the Lagrangian itself. If the action is gauge invariant, then the physics will be gauge invariant. All right, what do we do with this? We integrate it by parts. If you integrate a thing which is a product of one thing times a derivative of another, you can interchange which object the derivative acts on. Is this familiar to everybody, integration by parts? All right. It's an identity. Yeah, you get a surface term, but let's imagine integrating over all space-time to calculate the action over all space-time. So assuming that very, very far away the fields and the currents become 0, far enough away, then this is equal to minus 1 over E, the integral of epsilon times d mu j mu. Now, this is the change in this term in the action due to gauge transformation. You recognize this thing? Say it again? Yeah, d4x. d4x. But do you recognize this? That's the continuity equation. Remember the continuity equation. The continuity equation was the equation that said that if a charge changes in a box, the only way it can change in the box is by flowing through the surface of the box. A time dependence of the charge necessarily goes with a space dependence of the current, of the space components of the current. And that we distilled down, we studied it last time, and we found out that the continuity equation the local conservation of charge, was exactly this equation. d mu j mu is equal to 0. This is also the equation that says the time derivative of the charge density plus the divergence of the three-dimensional, just the usual current, should be equal to 0. The only way that the charge in a region can change is if there's a divergence of the current, which corresponds to current flowing out of the region, out or into the region. So this equation here is d mu j mu equals 0. The continuity equation is the necessary and sufficient condition for the action to be gauge invariant. As long as j is a conserved 4-vector, in other words, as long as it corresponds to a conserved flow of electric charge, the density together with the space component of the current, then this is gauge invariant. That's a beautiful fact, that, that gauge invariance requires the current to be conserved. We didn't even use any equation of motion for the current. We just used the fact or the assumption that the theory was gauge invariant. And from that, we derived that the continuity equation must be true. So this term, which is there if there are currents and charges, is gauge invariant under the assumption of the continuity equation. So let's just add it in, plus j mu a mu. Now that it's there, it will modify the equations for the electric and magnetic field. If we go back and calculate the equations of motion, there's now a new term. It's basically the right-hand side here of differentiating Lagrangian with respect to A. What do I get if I differentiate the Lagrangian with respect to A? I get J. So the answer is that there is another term on the right-hand side of the Maxwell equations which involve the current and charge density themselves. I'll just tell you right now that it's this and this. So if you go through this Lagrangian, work out the Euler-Lagrange equations, you find some additional terms on the right-hand side, which are the current, the charge density, and the current. Okay. I'll leave that for you to do.
There are sort of those two middle equations that we have in the Maxwell equation on the left.
Yeah, they follow just from the definition. Let me give you an example. Okay. Let's check del dot B equals 0. Now, I say that we don't need any equation of motion. It just follows from the definition of B. So let's see if we can prove that. Okay, let's write down the definition of the three components of B. So B3, or BZ, I guess, when I'm being very specific and working only with space components, I'll use X, Y, and Z. BZ was dx ay minus dy ax, right? BZ, x goes to y, y goes to z, minus dz ay, right? And finally, B, what I left out? By, xyz, dz, yxz, oops, dz ax minus dx ay. Now this is the definition of B. Now let's check. I've made no assumption whatever about the way that the A's are varying in space. In fact, I made no assumption because all I did was define something. Okay, now let's check whether del dot B is equal to 0. Well, why should it be equal to 0? I've made no assumption about the way A is varying. Let's check it anyway. That means we have to differentiate this with respect to Z. So let's differentiate it with respect.
They're all 0.
All right, let's check them. That means we have to take another derivative with respect to z and another derivative with respect to z here.
Well, there's no z components.
They depend on z. A, x, and y, and z all depend on z. They all depend on all the coordinates. So we get dz dx ay minus dz dy ax. This means multiple derivatives, second derivatives. All right, let's see if we can find, well, let's write them all out there. And then we have to differentiate this with respect to x. That means put a derivative with respect to x there, and another derivative with respect to x. And finally, a derivative with respect to y here. This gives us dy, and this gives us minus dy dx az. Was that it? Okay, let's see what we have. In particular, let's track this term here. This has an ay in it. It has dz dx ay with a plus sign. Here's another term with ay. It has dz dx, or dx dz. Doesn't matter which order. Right. Opposite sign. The order of differentiation is immaterial. And so this term and this term cancel. And so it goes. Let's see. Let's do one more. dz dy ax with a minus sign, dy dz ax with a plus sign. These cancel. And so it goes. All of them cancel. It followed from a definition of B. The structure of B was such, by the definition, B cannot be anything. If B, another way of saying it, incidentally, some of you may recognize another way of saying it, B is equal to del cross A. The divergence of a, that means B is the curl of A. No matter what A is, it's a rule that the divergence of a curl is equal to 0. For any A, the curl of A is B, and from that it follows that del dot B is equal to 0. So it just follows, this equation is not an equation of motion, it's just the definition of B, or a consequence of the definition of B. So is this one, consequences of the definition of B and E. Definition in terms of the vector potential. That's relatively easy to prove. I won't prove it. We did it for one of the equations. You can check out yourself that if you put in the definitions of B and E in terms of the vector potential, that this automatically is equal to 0. Contains a bunch of terms and they all cancel out among themselves. So half of Maxwell's equations are identities that follow from definition, and the other half are equations of motion that follow from the principle of least action. And it is necessary to these equations that the current is conserved. Incidentally, even if we didn't use gauge invariance, even if we didn't care about gauge invariance, but we stuck in, let's just look at something else. We have the Lagrangian, which is minus a quarter f mu nu, and then I put in plus j dot a, j mu, a mu. Let's work out, I've already worked out what the equation of motion is that comes just from the f mu nu terms. I'll remind you what it is. It was d mu, I think f mu nu was equal to 0. That was the equation, that was, how many equations are here? There are 4 equations here, one for each nu. And that was this equation and this equation. 4 equations, 1, 2, 3, 4. Now, if the right-hand side, if the vector potential appears undifferentiated in the Lagrangian, that means there's a right-hand side to the Euler-Lagrange equations. And what would it be? It would be the derivative of the Lagrangian with respect to A. The result is that there will be a right-hand side of this equation which will be j nu. Here is 4 equations with a right-hand side which contains the 4 vector of current. The time component involves the density, the charge density, that's this one. and the others involve the space component. That's the other components. But I just wanted to point out one thing. This is the equation of motion that followed from adding this term to the Lagrangian. Supposing I didn't know to begin with that J has to be conserved. Suppose I didn't know that J had to be conserved. I didn't know about all this gauge invariance garbage, and I just tried out this term in the Lagrangian. All right? I would get this equation of motion, and I would find out right now that J has to be conserved. We can check it. Let's just differentiate it with respect to x mu. In other words, let's take d mu of this. Oh, sorry, d nu of it. Let's differentiate with respect to x nu. That would be the continuity equation. Is it equal to 0? Well, it's equal to d nu d mu f mu nu. How about this? What is this? 0. 0, because it contains things like d1, d2, f12. I guess it's f21. But it also contains d2, d1, f12. When I sum over mu and nu, I get things like d1, d2, f21, and d2, d1, f12. These cancel because f12 and f21, the derivatives are the same. Second derivative with respect to 1 and 2, f12 and f21, they cancel. So we would have discovered right here that the equations of motion for F require that J is conserved. We don't really have the option of not allowing it to be conserved. The equations of motion force it to be conserved. So there are two independent arguments. They're closely related, but nevertheless, two independent arguments. One is gauge invariance. We did that nice little integration by parts, and we found out that the action was gauge invariant if F is conserved. But even if we didn't know that, if Weil had never taught us about gauge invariance, at this point, we would say Maxwell's equations, this set of equations over here, is inconsistent unless the current is conserved. We can check it right from here. We can differentiate this with respect to time, and we can take the divergence of some other equation over here, and we can check that, that the current will come out conserved. So that's a package, Lagrangian of a very simple form, simplest thing we could have written down.
I'm a little confused.
Yeah.
It doesn't mean individually that the charge density is conserved?
No.
And so
No.
how does the whole thing get conserved?
Charge
It means
density.
the sum of the charge density plus the currents is...
No. The time derivative of the charge density plus the space derivative of the current equals 0. Right. Yeah. This is more than just charge conservation. It's local charge conservation that tells us that the charge in a region can only change if currents are flowing into or out of that region. So it's a stronger thing than just saying the charge in the universe can't change. It tells us, what it says is the charge only changes in a region by moving into and out of that region. And that's what the continuity equation says. Where do we have it? I lost it. Well, d nu equals 0. So Maxwell's equations, either in this form or in this form, immediately tell us that the charge has to be conserved for the Maxwell equations to make any sense at all.
Force law, you'd add another term to the Lagrangian.
Well, it's actually buried in this term here, and we're about finished. If we take for the current associated with a single particle, and then we also add to the Lagrangian 1/2 mv squared for that part, we'll get the Lorentz force law. So we don't have time, but it's in there. It's in there.
You're
Yeah.
talking about the two independent arguments to get conservation.
Yeah.
One and
Well, they're not independent, of course, but yeah, but
One from the field equation, the other from the gauge invariance.
right. Yeah, that's right. So they're intimately tied together, and the principle of gauge invariance, of course, is much more general than just electromagnetism. We don't have time for it, but it appears in general relativity. It appears in Yang-Mills theory. Yes.
If you had monopoles, you'd have, and magnetic currents, then the middle two equations wouldn't be tautologies.
That's right.
You'd have to.
Right. So how can a tautology be wrong? Right. Exactly. Okay. That's right. That's right. The answer is that the right model for a monopole is the solenoid. Mathematically, the way monopoles are introduced into the theory is as infinitely long solenoids with magnetic field going through them and coming. Oops, I got to so that the net divergence of the magnetic field is zero by virtue of the fact that what comes in goes out. It's like it's like a little source of water over here. Yeah, you know what it's like. It's we have water coming into a puddle and causing the flow of water to diverge away from some point at the center. Well, if we saw that happening, we would say, hey, there must be a pipe coming in somewheres. Okay? If we account for the water that's coming in through the pipe and then going out away from the pipe, the divergence of the flow would be zero.
So you basically get rid of the monopole somewhere.
Get rid of the monopole and replace it by the end of a long solenoid. Right. So that is the mathematical way that monopoles enter into the theory. Now, are they really infinitely long? So this is called a Dirac string, incidentally. This is called a Dirac string. And under the right circumstances, which we won't have time for, but maybe another time, this string can be completely invisible. So, but the mathematics of it is to pretend that the monopole were connected to a long solenoid like this.
Black hole.
What's that?
A black hole.
What about a black hole?
Well, I mean, you can have an infinitely long trip into a black hole. So
What's that got to do with this?
Oh, I was just thinking that that could be the tube.
The black hole.
Yeah.
Well, not really. I mean, if you surround, the point is, if you surround the black hole, or if you surround the monopole, you should see a net magnetic flux coming out of it, which is equal to zero. So if the magnetic flux appears to be coming into or out of the monopole, there must be a secret hidden flow of flux away from that point. And it doesn't really matter whether this is a black hole or anything else. Yeah. Okay, ladies and gentlemen, thank you for your attention. And I will see you next year. Next year, we do some general relativity and black hole physics, and also some quantum field theory. Oh, no, wait, what did we say? Yes. And also some statistical mechanics. Yeah, general relativity and a little bit of black holes and all those interesting questions about gravity, which we haven't touched on at all. The quantum mechanics of fields. Quantum mechanics of fields is basically simple. It just says wherever you had a classical field, now replace it by a collection of quanta all moving together. So really, we've done it, but and statistical mechanics and thermodynamics and maybe a little about phase transitions and.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.